15 lines of Python, no libraries, and you've got a neuron that actually makes a decision. Here's how it works. A few numbers come in, each one gets multiplied by a weight that says how much it matters. A bias shifts the threshold up or down, and an activation function decides whether it fires. That's the whole thing, and that small piece is what every neural network is built from. Imagine you have two lists of numbers. One holds the inputs, the other holds the weights. To compute the weighted sum, you multiply each input by its matching weight, and then add all those products together. This operation is called a dot product, and it measures how much the input aligns with the weight vector. If the input points in the same direction as the weights, the sum grows large. If they point opposite, the sum shrinks or becomes negative. If this is useful, subscribe. The whole series builds on it. The bias is a constant term that shifts the weighted sum up or down. Think of it as a head start in a race. It does not change how fast any runner moves. It changes where they begin. A positive bias makes it easier for the neuron to fire, while a negative bias makes it harder. By adjusting the bias, we can set the neuron's activation threshold without changing any weights. This gives the model extra flexibility to fit data. So far, we have built one neuron, but the goal is to connect many of them together. Here is the problem with that. If we only combined inputs with a weighted sum and bias, stacking many neurons would still produce just a linear function, no matter how many layers we add. Nonlinearity acts like a faucet that stays closed until pressure reaches a certain point, then opens and lets water flow. By applying a nonlinear activation function after the sum, the network can learn complex curved patterns that straight lines cannot capture. A neuron first computes the weighted sum of its inputs, adds the bias to shift the result, and then passes that total through an activation function. Think of it as mixing ingredients, inputs according to a recipe, weights, adjusting the seasoning, bias, and finally applying heat, the activation, to transform the mixture into something new. This three-step process yields the neuron's output. Let's see the neuron in action with concrete numbers. We'll define 3 inputs, 3 weights, a bias of 0.5, and use the sigmoid activation. The program computes the weighted sum, adds the bias, applies sigmoid, and prints the resulting activation. This demonstrates how changing any number changes the neuron's decision. We'll also show the intermediate weighted sum and bias shifted value to see each step. While sigmoid squeezes values into a 0 to 1 range, another popular choice is the ReLU, which stands for rectified linear unit. Imagine a water pipe that lets flow only when pressure is positive. Any negative pressure is blocked completely. ReLU does the same with numbers. It outputs the input unchanged if it's greater than 0, and outputs 0 otherwise. This simplicity makes ReLU fast to compute and easy to implement. To reuse a neuron many times, we bundle its weights, bias, and activation choice into a single object, just like a reusable appliance that comes with preset dials. A class stores the parameters as attributes and provides a forward method that computes the output for any given input vector. This encapsulation lets us create many neurons with different settings while keeping the code clean and easy to extend. In practice, we often initialize a neuron's weights to small random numbers so that each neuron starts with a different perspective. Using Python's random module, we can generate a list of weights drawn from a uniform range, say -0.5 to 0.5. The bias might also be initialized randomly or set to 0. This randomness helps break symmetry and allows the network to learn diverse features. By changing the weights while keeping inputs and bias fixed, we can see how the neuron's response shifts. Think of the weights as knobs on an audio mixer. Turning one knob up amplifies that input's influence, turning it down reduces it, and a negative knob flips its effect. Note that we are setting these knobs by hand, so the neuron is not learning anything yet. We are configuring what it detects. In the next chapter, we will see how an algorithm finds these numbers on its own. Instead of writing an explicit loop for the weighted sum, we can use a list comprehension paired with sum to compute the dot product in one readable line. This is a concise, pure Python expression, not true vectorization. Libraries like NumPy get their speed by running array operations in optimized compiled code, which this does not do. What it does give us is the exact same mathematics in a form that makes the neuron's forward method much easier to read. To see the impact of the activation function, we create 2 neurons that share the same weights and bias, but use different activations, one with sigmoid, the other with ReLU. We feed the same input vector to both and print their outputs. The sigmoid neuron squashes the result between 0 and 1, while the ReLU neuron either passes the positive sum unchanged or outputs 0, illustrating how nonlinearity shapes a neuron's personality. That is, the neuron, weights, bias, and activation. From here we build toward embeddings and how a model represents meaning at all. Subscribe to follow AI from scratch.